So let's see example 1. You have to deduce which species is the strongest oxidizing agent. So strongest oxidizing agent is going to have the most positive electrode potential. So it is itself going to be reduced, and it's going to cause oxidation. So the species that is itself being reduced is Cl2. Next, the species that can reduce Cl3+, for it to be able to reduce the Cl3+, it should have an electrode potential which is negative, but which is higher in value than the electrode potential of Cl3+, the reduction of it. So it's going to be this one, which means that Cl3+ is going to be reduced, therefore the other species is going to be oxidized. So the species that causes the reduction of Cl3+ is itself going to be oxidized. So Al is the reducing agent. Now the species that can reduce SN4+, if it can reduce SN4+, the electrode potential should be more negative, but it should be less than 0.74. So it's this one. But since we're looking for a reducing agent, so the species itself is going to undergo oxidation. So it's cobalt solid. Then you have to explain the meaning of the negative sign when it's connected to a standard hydrogen electrode. So this means that the electron flows from the CO2 plus half cell. So this acts as the anode, and the electron will flow to the standard hydrogen electrode, which acts as the cathode. That's why it's negative. If it's positive, means that it's the standard hydrogen electrode that's acting as the anode. For you to deduce the spontaneous reaction means that you have to do the working so that electrode potential is positive. So the electrode potential that's most positive is going to be the cathode, and the one that's negative, more negative, it's going to be the anode. So this is the anode, this is the cathode. We're going to write the overall reaction. So cathode equation stays the same, anode the equation is flipped. Here you need to multiply by 2 because there's 2 electrons here. So this is a spontaneous reaction that will occur. Next, you need to identify the positive and negative electrode. So the positive electrode is the cathode. So this is the positive electrode. And the negative electrode is the anode. So nickel solid and nickel 2+. Next, you need to identify which one is being oxidized and which one is being reduced. So oxidation takes place at the anode. So this is the anode. At the anode, you'll have oxidation. So the species being oxidized is nickel solid. And at the cathode, you'll have reduction. So the species being reduced is Ag+, aqueous. Deduce the overall cell potential. So it's electrode potential of cathode minus anode. So electrode potential reduction minus electrode potential oxidation. And then you need to find Gibbs free energy. So delta G is minus N times F times electrode potential of the cell. Number of electrons from the equation is 2. So minus 2 times Faraday's constant times electrode potential. This is in kilojoules. You have to draw the label diagram of the cell. So the 2 half cells are given under standard state conditions, so you can put in the concentrations. So this is the diagram. For magnesium half cell, electrode potential is negative, and for the silver half cell, it's positive. So electron will flow from anode to cathode. So this is going to be the anode here. So we have shown the direction of flow of electrons in the external circuit. You need to deduce the potential of this cell. So overall electrode potential of cell is reduction minus oxidation. So reduction will take place at the cathode and oxidation will take place at the anode. So this is the overall electrode potential of the cell. Now predict the change in electrode potential when the concentration of Cu2 plus increases. So when concentration of Cu2 plus increases, according to Le Chatelier's principle, the equilibrium will shift so as to decrease this concentration. So this increases, therefore the equilibrium will shift so that it decreases. So it's going to shift in the forward direction so that this is used up. So equilibrium will shift to the right. In the process, the electrode potential of the Cu2 plus Cu half cell is going to increase. So this value will increase over here. So when this value increases, the overall electrode potential is going to increase. So eventually it increases. You have to deduce the equation for the spontaneous reaction. So the two half cells are provided. You have one half cell here and another half cell here. You're going to use the data booklet. Look for the equation corresponding to this one first here, and then for the other half cell. So for a spontaneous reaction, the one that's more negative is going to be the anode. So this is going to be the anode. This is going to undergo oxidation. Therefore, this is going to be the cathode, and this is going to undergo reduction. So the cathode stays as it is, and the anode is going to flip. You have to adjust the number of electrons, multiply by 6. So this is going to be 3. And you can add the two equations. The electrons will cancel out. So this is the overall equation, and if you want, you can calculate the overall cell. For the next question, you have to use redox potential to show whether SN2 plus can reduce Fe3 plus. So the reduction reaction, you'll have Fe3 plus turning into Fe2 plus. So which means that SN2 plus is going to act as the reducing agent. So itself, it's going to be oxidized, which means we're looking for SN2 plus to be at the anode, and this is going to be the cathode. So I'm going to look in the data booklet, look for the equations. So these are the two equations. So this one should be the reduction reaction at the cathode, and this one should be the oxidation reaction at the anode, which means that this equation will flip. Now let's see whether it's possible, whether the reduction reaction is possible. So we'll find the electrode, the overall cell potential. So reduction minus oxidation. So that's going to be positive 0.62 volts. Shows that it is possible. Now, if it was let's say the last question, you have to show that Cu plus coming in contact with water can undergo disproportionation. Disproportionation means it's oxidized and reduced at the same time. So in the same equation, you have Cu plus getting oxidized, so turning to Cu2 plus, and Cu plus being reduced. that is turning to copper. So on the in the data booklet, we're going to look for equations where Cu plus is being reduced. So this is the reduction equation in the data booklet, and then I'm going to look for one where there is Cu2 plus electron giving Cu plus. So I have Cu plus in both equations, so that one is going to be reduced, one is going to be oxidized, which means that this equation is going to flip. So I have the two equations. This is for reduction, this is for oxidation, already flipped. Electrons cancel out, so I have 2 Cu plus getting converted to copper solid and Cu2 plus aqueous. So here you have this reaction, which is reduction, and this reaction, which is oxidation. So this is disproportionation, oxidation and reduction at the same time. And if you calculate the overall cell potential, this is going to be the reduction minus the oxidation. So this is positive, which means that it is possible, it takes place. Therefore, we have shown that oxidation state of Cu changes from +1 to 0 and +2 in the same reaction. Therefore, this is disproportionation. With this, we end with voltaic cells.